So today we're going to talk about Monte Carlo methods as a way of evaluating our policies as well as learning policies. So last time we've looked at dynamic programming type of algorithms, policy iteration, value iteration, but last time we were making an assumption that we know something about our transition function, right? So we know something about the model, that we can compute expectations exactly. So today we're going to look at Monte Carlo based methods, and there is also a number of good resources online. If you look at Rich Sutton's class on reinforcement learning as well as David Sitwell's class on reinforcement learning, some of the material is going to be borrowed from their lectures. Okay, so let's get into Monte Carlo methods. So the key idea behind Monte Carlo methods is that you're trying to learn the value function and the policy from experience, okay? And the Monte Carlo methods basically uses the simplest possible idea, which is the value equals mean return, right? And I'll make it a little bit more precise what that means. But essentially, you're simulating your model, and then you're trying to get some average return. Now, Monte Carlo methods can be used in two ways. There is something called model-free methods, which basically you don't necessarily have to have a model of the environment, and you still get optimality, which is important, and also simulated. You only need a simulation, not a full model, right? You need to be able to simulate something, but not necessarily having a full model of the world. And we'll see some examples of that as well. So Monte Carlo methods essentially learn from complete sample returns, right? You're simulating your system forward, and you're trying to estimate what the return is. It's also defined only for episodic tasks. Remember what the episodic task is? It basically means there's some terminal state. You run your simulation forward up until there's some terminal state and you stop. So all episodes must terminate, right? It's no way for you to do bootstrapping. So let's look at the Monte Carlo policy evaluation. So the goal is to learn some value function for a state given a particular policy pi from episodes of experience on the policy pi, right? So what happens is that you start at a particular state, you choose the action according to your policy. In this case, the policy specifies a distribution of possible actions, so you sample from your policy an action, you take an action, you get the reward, you get the next state, again, you take an action according to your policy, you get the reward, you get to the next state, right? Up until you reach some terminal state, S sub k. So now remember that the return is the local discounted reward, right? So you start at a particular time t, and then you're basically looking at discounted reward into the future up until some time capital T, where you're basically reaching some terminal state. And just another key equation to remember is that the value function is expected return, right? So it's expected value of your return, which is discounted return going forward, starting at a particular state S and taking expectation on the policy pi, right? The policy pi is telling you what actions you need to be taking. Now, the Monte Carlo policy evaluation essentially uses empirical mean return instead of expected return. Okay? Now, in many cases, remember in our last class we were using dynamic programming. If we knew something about the transition function, we could evaluate this expectation, at least one step look ahead. But here we're basically going to be using empirical mean return instead of expected return, right? So we only need to get samples as opposed to actually computing what the transition function is. What's the next state given the previous state and the action. So in terms of Monte Carlo policy evaluation, so there are two things we can do. One idea is to average returns observed after visits to S. So one idea is something that's called every visit Monte Carlo, which is the average returns for every time S, when every time S is visited in an episode, right? So for example, you start at 2, for example, you go to 3, you come back at 2, you go to 3, you come back at 2, and then 3 and 4, and then you reach your terminal state. So every visit Monte Carlo would basically average the returns, right? So you've started at state 2, in this case 3 times, right? Because you visited it 3 times. So you visit it and you're basically counting, once you started at that point, what's the return? There is also first visit Monte Carlo, which is average return only for the first time S is visited in an episode. So the first time you start at, let's say, 2, and then you only considering the expected returns or the final returns once you reach the final state, even though you can come back to the same state multiple times, right? Both converge asymptotically, right? Do you guys see what I mean? Right? The first visit Monte Carlo is basically you start at the state, you simulate your system forward up until you reach the terminal state, and then you're looking at your discounted rewards. Every visit Monte Carlo basically says every time you visit that particular same stat S, you just keep multiple instances, right? And then you're averaging all of them. Typically, in many cases, most time, the first visit Monte Carlo is commonly used method, right? You start a particular state, you run your system forward up until you reach the terminal state, and you look at the discounted reward for that particular sequence. So here's a little bit more detail of the algorithm. It's a very simple algorithm. To evaluate state S, the first time step T, that state S is visited in an episode, you do the following. You increment the counter, right, the number of times when state S is visited. Again, we remember we're working in discrete spaces right now, so we have a finite number of states, and you increment the total return, right? Anytime you get some reward at a particular time step T, you add it to your overall reward, right? And then the value is estimated by the mean return, right? Which is kind of what your average return is versus how many times you visited a particular state, right? And then by law of large numbers, you can basically say as n sub s goes to infinity, as you visit the state multiple times, you will converge to the optimal value, right? So this is, at the high level, all it's doing is it basically saying, if I start at a particular state, right, and I run millions of simulations. For every single simulation, I get the return, right? And if I average it over millions of simulations, I'm going to get a pretty good estimate of the value of the state. And as I run it, the number of simulations go to infinity, I will recover the correct value of the state, okay? Correct value function. And then for the every visit Monte Carlo, it's basically exact same thing, but then instead of saying the first time you're starting at a particular state S, every time step T, that state S is visited. Right? So you're just basically averaging over more things. Ultimately, both algorithms are about the same. Probably every time step T is a little bit more efficient, but otherwise it's asymptotically they both give you the right answers. Any questions? It's very simple. It's just basically just running your simulation forward and just averaging your overall returns. So here's an example. Let's just look at one example. How many of you know how to play blackjack? A few. Okay, good. Not that many, so maybe you can help me out here, because I don't know how to play the blackjack. So the objective is you have your card sum be greater than the dealers without exceeding 21, right? So there's a dealer and there's you, right? And you want the sum of your cards to be greater than the dealers, but not exceeding 21. If you exceed 21, you basically lose. So in terms of the number of states, there are 200 states. Your current sum, which is any number between 12 and 21, and the reason why it's not below, because if you have, 6, you always hit, because you always want to get, a card so that you hit, so that you are in this range. The reason why you're in this range is because if you have 12 and you hit, you might get to 22, right? Because like a face card is 10, 10, and such. And then you're also looking at the dealer's showing card. The dealer has a card, right? Could be ace or 10, any sort of one of those cards. And then there's another part of the state is that do I have a usable ace? So apparently in the blackjack, your ace can be counted as 10 or 2 or 1? 1 or 10, right? So you can 1 or 11. There you go. So it can be counted as 1 or 11, right? So you basically say, do I have an ace or not? The reward can be set up as +1 for winning, 0 for the draw, and -1 for losing. And the action is you either stick, basically say, I'm not receiving any cards, or you hit. You basically want to receive another card. Okay? So depending whether you have a usable ace, depending whether what your opponent is showing, because right now you're making these decisions of whether to hit or stick. And imagine that you have a policy, right? Your policy is always stick if your sum is 20 or 21, else you always hit. That's not a good policy, but let's say that's your policy. So you want to evaluate, you want to do compute the value of the state. You want to look at all of those 200 states and say, what's the value of being in one of those states? Okay? And this is just some examples of using Monte Carlo policy, right? Which is to say that I start at any one of the states, right, out of any one of those 200 states. So here you're showing dealer showing from A to 10. This is the player sum from 12 to 21. And now you're computing what's the value of the state. So obviously you can see that if your policy is to hit always, unless you have 20 and 21, then pretty much all the states are pretty bad. I think they're like -1, right? And if you're kind of like in 20 and 21, then it's a pretty good state to be in. Because if you have 20 and 21, you most likely will win. Otherwise, if your policy is always to hit, if you're in this range, you most likely will lose, right? Because you're kind of like ignoring what the dealer is showing. You just basically say, I have just one policy, right? So you can see by using Monte Carlo. How to use Monte Carlo methods? Well, in this case, you start at a particular state, dealer's showing something, your sum is showing something. Let's say you start here, and then you just draw the card and you hit, right? And then you see, did you lose or did you win? Right? So you do it over all possible states. Okay? And after 500,000 episodes, right? So obviously you can see it requires a lot of episodes to figure out what the value function is for your current policy. Okay? So if you think about Monte Carlo, then the entire rest of the episode is included, right? You're also making only one choice for each state. And this is unlike dynamic programming, right? The reason why is because when you're simulating for it, you're basically at a particular state and you're saying, do I take an action, or I sample the action and I take this action? I'm not going back and saying, well, what would happen if I took this other action, right? Or what would happen if I took this other action? So generally when you're simulating it forward, you're just simulating one action. So there will always be something that's called explore-exploit dilemma. And we'll come back to that later, right? Because you want to design the algorithms that you don't want to take the same action always, right? Without exploring what other actions, what would happen if you took a different action. It doesn't bootstrap from successive state, unlike in dynamic programming where we're computing expectations and as opposed to just doing samples. The value is estimating by the mean return, and the time, the most important, is that the time required to estimate a state doesn't depend on the total number of the states. And this is the beauty of Monte Carlo methods. For any of you, if you've seen Monte Carlo methods before, if you've been looking at either Monte Carlo approximation of the high-dimensional integrals or using Markov chain Monte Carlo methods, these methods can have high variance, but at the same time, the estimate itself doesn't depend on the number of states, right? Which is kind of nice. So you can basically have a very large number of states, and these kinds of estimates will give you reasonable estimates of your value function. Later on, I think we're going to look at something that's called Monte Carlo tree-based search, which is something that's heavily used in games like backgammon, back 20, 30 years ago in AlphaGo, so and such. These are Monte Carlo-based strategies. One thing that I also want to point out is that in many cases we're going to be estimating the mean function incrementally, right? Obviously, in these cases, you start at a particular state, you go all the way to the terminal state, you compute your value, and you repeat it multiple times, and then you take the average. But we can also use estimate the mean function using this incremental strategy, right? And the means mu1 of some sequence can be computed incrementally, right? And this is just a little bit of a math that essentially shows that to estimate the mean of mu sub k, it's equivalent to taking a mean at mu sub k minus 1 plus taking the difference between xk minus mu sub k minus 1 divided by 1 over k. Okay? It's the same thing. So once you have mu sub k minus 1, you want to estimate the next mean, you just follow this equation here. Okay? So we'll come back kind of using the same thing again. So for example, here to update the value of the state incrementally, after you've seen an episode, you start at a particular state, you take an action, you get the reward, and so forth, all the way up to some capital T, some terminal state. For each state, with return, G sub T, again, you're basically counting how many times you're visiting that particular state. And then you're updating the value function as the value function plus the previous estimate plus what the mean is, what the estimate of the mean is. Okay? So it's kind of interesting. Notice that at some point, I guess, if your value of your state is the same as your return, then this term is going to be 0. But because of the variance, it never is 0. Also, it's interesting to note that in non-stationary problems, as your environment changes, it can be useful to track a running mean, or sometimes you can use exponential moving averages. So in this case, you're sort of using this particular way of estimating, right? Where alpha is some hyperparameter. So you can pay attention more to recent history and forget the old one. Yes.
The current value is the previous value of
Yeah. You can think of it as t minus 1, right? So it's like this is the new value, this is the old value. So again, at the hindsight, all you're basically doing is you're rolling your simulation forward, and you're just computing empirical mean. That's all you're doing. Very simple. Okay? So it's a very naive, and we will see later in our class, I guess in Wednesday's class, is that sometimes doing this is not very efficient. There are better ways of doing this, but nonetheless, this is an unbiased estimator. Right? It basically means that you're simulating it forward. You will, in expectation, converge to the correct value. You can also do the same thing to estimate the action values. You can also estimate Q functions. And again, the Monte Carlo methods, just to point out, is useful when the model is not available. You don't know what the model is like, but you can generate samples from the model, right? So in many cases, like if you think, for example, in playing Atari games, which is something that you will do for your second homework assignment, is that you have a state, you take an action, and then the environment gives you the next state, right? The game engine gives you the next state, right? So you not necessarily need to model what the environment looks like, it's just the environment gives you the next state. So just a reminder what the Q value, it's an average return starting from state S and action A following policy pi, right? And remember, that's the definition of the Q value. We've looked at this couple of classes before. It's an expectation under the policy as well as the state. So it's an expectation under this quantity here. And it's the reward plus the value of the successor state, right? And remember, we've talked about this, that the Q values really decomposes into two pieces. The first piece is what the reward is by taking this action. The second piece is how good the next state is. And obviously here you're averaging over all possible states, all over possible rewards if you have some stochasticity in your reward signal. Okay? But it's a sort of expectation of the expected value of what the reward you get versus the expected value of how good the next state would be averaged over all possible states that you can get to, according to your transition function. And again, we can do exactly the same thing here using Monte Carlo sampling, right? We're going to be approximating this expectation by just doing samples from your policy pi, right? You're in particular state, you take an action A, and then you get the next state, and you get the next action, and the reward, and so forth. So it's exactly the same thing. It converges asymptotically if every state action pair is visited, right? So that's also a caveat that, obviously you need to start at a particular state and take a particular action. You have to make sure that every single state and every single action is visited to converge, which makes sense, right? There's a particular state you never start from or you never visit, you don't have a Q value for that state. And one way to sort of ensure that you have convergence is to do something that's called exploring starts, which is every state action pair has a non-zero probability of being a starting pair. Right? So you basically just put maybe a uniform or whatever distribution you want to put, just to making sure that there's some probability that you'll start at every single state and you take every single possible action. And now you can do something similar to what we've done in the last class, right? You're first doing policy iteration step, which is the policy evaluation. Given the current policy, you evaluate your policy using Monte Carlo methods, right? So you evaluate, you compute the values of the states, and then there's a policy improvement step, which is greedily, greedified with respect to the value or action value function, right? So it's exactly the same strategies we've seen before. The only difference is that here we don't have access to the model, but we can only generate samples from the model, right? So for the model-free environment, it's a very commonly used method. Obviously, if we knew something about the model, if we knew something about what this probability is, and we could compute this expectation, right, then we could be using dynamic programming to be able to evaluate these values much more efficiently. Here, we're essentially using Monte Carlo sampling to do the same thing. And again, just to remind yourself what the greedy policy is. So here, for any action value function Q, we're going to be constructing the following greedy policy. For each state S, we're going to be deterministically choosing an action with the maximum action value function. So if you're estimating Q using Monte Carlo evaluation, then you can always have a policy that's better by just taking a max, taking an arg max. The Q function, right? Pick an action that gives you the best Q value. And then policy improvements, you're going to be constructing, for each one of those steps, you're going to be constructing the new policy pi k plus 1 as the greedy policy with respect to Q pi k. Okay? And here's a little proof. There is a little proof that basically showing that if you do this, ultimately you will converge to the optimal policy, right?
Is that if we're going to the next step, or are you taking the maximum action value with respect to the whole game?
Over the whole. So here you're taking for every single state, you're taking the optimal action or the best action according to your current value Q for all states, right? Because the policy is defined as a function of the state to the action. So you kind of do it for every single state.
So it's not the same as the myopic.
No. It's a global thing. You're doing it for every single state. And this is just a little proof, right? Two-line proof that basically saying that this greedified policy meets the conditions of policy improvement, which is essentially says, what is pi k plus 1? It's argmax over Q, right? Which is the same as taking the maximum of the actions from the Q function according to policy pi k. Think of it pi old. it's always greater than just the value of q and taking the policy pi k, right? Because it's the maximum one, you're taking the best one. And this is always greater or equal to the value of the state. And so it must be better than pi k. So the q value will increase. And eventually you will reach the optimal policy. Now, this assumes exploring starts, right? This is on the assumption that every single state action is visited. You have non-zero probability of visiting every single action state pair. And you also have infinite number of episodes, right? Because remember, Monte Carlo is basically saying by the law of large numbers, as the number of episodes goes to infinity, you will recover the correct value function for Markov policy evaluation, right? So it basically, under those conditions, in practice, it typically works fairly well if you don't do it for infinite number of episodes, obviously. So here's a little code, I guess, for doing Monte Carlo evaluation. So let's just go through it because it's a little bit easy. This is how you would code it. Again, so far, for the first 5 or 6 lectures, we're going to be looking at what I would call traditional reinforcement learning algorithms, where you have finite number of states, a finite number of actions, and we're just looking at the algorithms, right? Later on, we're going to be extending it to continuous actions, continuous states, and such. So it'd be a little bit more interesting, but the underlying algorithms will remain pretty much the same. So let's look at what happens here. So for all states and actions, we initialize our Q function to be arbitrary. Typically, you'd set them to 0 or some numbers. The policy is arbitrary also. Think of it as a uniform. So initial policy is just take random action and then return, starting at state S, taking action A is just an empty list. Okay? And then you basically repeat forever. You choose a state and an action such that all pairs have probability greater than 0, right? So that basically ensures that you reach every single state in action. You generate an episode starting from S0 and A0 following pi. So what that means is that your particular state, take a particular action, and then you just run your episode following policy pi, right? You take an action, the environment gives you the next state, reward, you take another action, and so forth. Think of a robot that you basically say, you have a set of actions, and then just basically say, start at a particular state, particular action, and just roll out using your policy. For each pair SA appearing in the episode, G is the return following the first occurrence of SA. You append G to the returns, and then your Q function is just the average of the returns. Okay? This is just basically saying every time I'm in a particular state and I take a particular action, if I go all the way to the terminal state, what kind of reward would I get? Right? That's exactly what's happening here. And then for each S in the episode, you just compute the policy using argmax of the Q values. Okay? Now, you can imagine that this could be very inefficient. If you have a very large state space, you have large number of actions you need to take, obviously, this would be very expensive to do, right? So then the question is, can you do something maybe about the policy? Because if your policy is completely random policy, it's going to take you a while to learn something about the policy, right? But nonetheless, asymptotically, you will get the optimal policy, okay? So here's what happens with exploring starts. This is the blackjack example. This is actually learning the policy as you proceed. So you evaluate, you greedify, you evaluate, you greedify, and after a while, this is what the optimal policy would look like. If you have a usable ace, then I guess this is the dealer showing, and this is your number of, your current number. So it's basically saying, if you are in this range, you hit. If you're in this range, you stick, if you have a usable ace. Okay? And here it's a little bit more interesting. It's basically saying that if you don't have a usable ace, if your dealer is showing this, you basically stick. If your dealer is showing this, and this is your sum, you basically hit. Okay? So there's some more strategy that you can kind of figure out what to do. right? And this is again done by, initially your policy could be some random policy, and you do evaluation of, you compute the Q function using Monte Carlo, you greedify your policy, you recompute your Q function, greedify the policy, and so forth, up until you're converging to something more interesting, like what you're seeing here. It looks pretty reasonable to me in terms of, you know, like if your dealer is showing something like this, you probably, and you have 12, you might want to hit. Right, so that's exactly what the optimal policy would look like. Okay, now, one of other one of the other things that we're going to talk in this class is on-policy evaluation or on-policy control. In this case, on-policy Monte Carlo control. So on-policy is basically when you want to learn about the policy you're currently executing. And, you know, how do you get rid of exploring starts, right? Because the whole thing about Monte Carlo methods is basically telling you need to be able to evaluate, to visit every single state and take every single action. But imagine you're running a policy right now, and your policy basically says, I never take an action turn left, for example. How do you avoid that? Because the policy must be soft, eternally soft. You always must have some non-zero probability of taking a particular action and being in every single state, right? So how do you achieve that? Well, in many cases, and we'll see this again and again in this class, is one very simple way of doing it is the epsilon soft policy. Or you're basically saying that the probability of an action for the greedy one, you take the maximum, but for the non-maximum one, there is some epsilon probability that you're going to be taking that action, right? So it's epsilon divided by the number of possible states. So imagine you have 10 actions you could take, right? The Q value is telling you take action first, because it's the maximum one according to your Q function. But then you're saying, well, with probability 1 minus epsilon, I'm going to take this action. With probability epsilon, I'm going to spread out my probability across the remaining 9 actions, right? So you're basically spreading some epsilon across, you know, taking all other actions. And this is done for, you know, you can think of it as an exploration that you need to do. It's similar to the general policy iteration. You move towards the greedy policy, but in this case, you will converge to the best epsilon soft policy, right? This epsilon basically maintains exploration. And this is probably the easiest and the most commonly used setting in practice. Again, for example, for your second homework, you're going to be building some Q-learning algorithm, and you'll find out that actually this epsilon matters a lot. In fact, initially, you set this epsilon to be quite high, which is for sufficiently large epsilon, you're basically taking random actions, right? And as you go through the process of learning, you decrease this epsilon, so you're making your policy be more and more, you're doing more and more exploitation and less exploration, okay? And I believe later on in the class, we're going to look at some other ways of doing exploration, because this way of doing exploration is actually pretty bad. There are settings when, you know, you don't want to take random actions, or you don't want to be kind of like, if you're at the edge of the cliff, right, then you don't want to once in a while just pick a random action to do it, right? At the same time, you might want to do it once or twice just to make sure that you're actually jumping off the cliff. Maybe jumping off the cliff would be a good idea because, you know, you jump and you go to the next level, for example, in the game, and you get a big reward. Right? Maybe that would happen, in which case you need this, this epsilon. But in general, that might not be a good idea. Yes?
You say you decrease the epsilon at the node, right? But do you necessarily have to decrease it initially, or is that for implementation purposes, decrease the epsilon?
So in theory, your optimal policy would be deterministic policy, right? So for any epsilon that you preset, you will converge to the best epsilon of policy. Right? In practice, what happens is that if you choose your policy initially to be deterministic policy, and you just start evaluating it using deterministic policy, you will not converge because you don't have enough exploration. You need to do exploration. And particularly for on-policy learning, right? So you're not running episodes of tasks or of sort of, you start at the state, take an action, you run it. Imagine a system that just continuously runs, right? And you want to learn something from it. In this case, you need to introduce this epsilon greedy because you need to make sure that you are visiting every single action. And you have to put constraints on your transition operator that basically tells you that you should be able to visit every single state. If you don't, you will not converge to the optimal policy. Obviously, right? That should make sense. If you never visit state number 1, how could you converge to the optimal policy? So this is on-policy Monte Carlo control. It's pretty much the same as before. Let's quickly go over it. So you initialize all states and actions. You initialize the returns. Your pi, your policy is an arbitrary epsilon of policy, right? So you always have some probability of taking a random action. You generate the episode using pi. For each pair appearing in the episode, G is the return following the first occurrence of SNA, and so forth. So you evaluate your Q function. But then for each S in the episode, you compute the maximum, you compute the best possible action to take according to your evaluation. You compute the best one to take, but then for all actions, you're basically saying, well, with probability epsilon, epsilon basically for all the other actions that are not optimal, just take the action. And then for the remaining ones, it's just a calculation of how much probability mass you have, you take the optimal action, right? And the epsilon parameter will tell you how much to control exploitation, which is the best optimal action you should take, versus exploration, right? How much explore you want to do. And this idea of exploration, exploitation is actually a pretty big area of research in reinforcement learning. If you look, for many of you who are interested in, there's something called bandit problems or contextual banding, K-arm bandit problems. This is a very, key, or I would say even open area of research of how do you trade off exploration versus exploitation. Yes? If you keep the K best states, it still might not guarantee that you will visit all the states. Or if you keep the K best actions, there's still not guarantee that, the key thing that you want to do here is that you want to make sure that you visit every state action pair, right, throughout the learning process. Because if you don't, imagine like here, you've initialized this thing to 0. So if you never visit state and action, then this Q function is always going to be at 0, right? And you will never converge to the optimal one. So that's the reason why you need to do that. So let's look at the summary so far. So Monte Carlo has several advantages over dynamic programming, right? We can learn directly from interaction with the environment, right? So the environment supplies us the next state. No need for full models. We don't really need to have a full model of the world, right? Which is both an advantage and disadvantage. If you had the full model of the world, you would be better off using it because you can compute exactly, using dynamic programming and just average over all possible actions and average over all possible transitions to the next state, and you would converge much faster, right? But in general, even in real world settings, you never have the complete model of the world. You don't need to learn about all states at the same time, right? As long as you have a guarantee that every single state action is visited asymptotically, you will get the right thing. And generally, it's less violated by, it's less harmed by violating Markov property. So later on, we'll see that in the class. So if your world is not necessarily Markovian, Monte Carlo is pretty robust to that, much better than for example, dynamic programming. Yes?
Slide. What's the intuition behind dividing by the size of the action space? So you
Here?
can choose an epsilon that is, just epsilon. Yeah.
I think it just basically tells you that no matter how big your action space is, whether you're taking 2 actions or 20 actions or 1,000 actions, this is just saying that how much of a probability mass you want to allocate for taking non-optimal action. That's all. You can define epsilons to be however you want to define them.
Greedy actions and non-greedy actions, and then divide
You
epsilon
can do
by
it,
that.
but this is kind of like one-to-one correspondence between both of these formulations. You can divide it greedy and non-greedy, or like optimal best action versus non-best actions, and then kind of like you're just allocating mass across those. This is just one way of doing it, right? Which doesn't depend on the number of total actions, right? Because you're basically saying, with probability 1 minus epsilon, I take the optimal action according to my Q value. With probability epsilon, I take a random action. That's all. And Monte Carlo methods, they do provide an alternative policy evaluation process, right? Now, one issue to watch out is the maintaining sufficient exploration, right? So this is one thing that you have to do. Because with Monte Carlo, if you don't visit certain states, you don't take certain actions, then you might not converge to the optimal policy, right? That's an issue. With dynamic programming, if you know what the world is, you know what the transition function is, you know what the probability of the next state given the previous state in the action, you can take an expectation with respect to that. It's equivalent to marginalizing over all possible states that you could take, or over all possible actions that you could take. So here you have to maintain sufficient exploration. Now, let's also look at the off-policy methods. So here the idea is that you want to learn the value of the target policy pi from experience due to behavior policy mu. Okay? So you have 2 different policies. For example, pi could be the greedy policy, and maybe ultimately the optimal policy, while mu is exploratory policy, for example, epsilon self policy. Okay? And this is something that's used a lot in practice. The reason why is, imagine you have a production system running, and your production system is running it's running target policy pi, right? And then you build a new policy mu, and you go to your boss and say, I have a better policy. Like, imagine you're working for Google, and Google uses reinforcement learning. Let's say they're using reinforcement learning. I don't know where they're using reinforcement learning. Let's say you're using reinforcement learning to place ads on your screen, right? And imagine there is a policy that basically looks at the context, looks at the state, and says, this is the ad that I want to place over here, right? And your reward is, how many times users click on that ad. The more users click, the better reward you get, right? So that's a reinforcement learning problem. Now imagine you are an engineer or researcher. You come up and you say, I have a better policy mu. Let's put it in place. Now, as a manager of the ads group, would you switch policy pi to policy mu? What do you think? How many of you would switch? How many of you wouldn't switch? Good. Most of you wouldn't switch, and you shouldn't. Because how do you know that policy mu is better than policy pi in general, right? And that generally is the case, because if you're running something in production, you can't just switch it to another policy. Because if a researcher was wrong, you're putting something in the production and it's like, boom, you've just lost, let's say, hundreds of millions of dollars, right? You can't do that. So the question then comes, how do you learn the value of the target policy pi from experience due to behavior policy mu? Okay? So in general, to do this, you only require coverage. So for example, your policy mu should generate behavior, should generate samples that covers or includes policy pi, right? This condition has to hold. This policy should be non-zero for every state action in which mu is non-zero. Okay? And you can see, because if you want to compare both, support for both distributions is different. It's very hard to compare both. There are ways of doing it, but here we're not going to do that. And so the idea is to use something that's called importance sampling, which is a very simple idea. You basically weight each return by the ratio of the probability of the trajectory under the two policies. Okay? So the intuition should be as follows. Let's say that, you know, the existing system places a net at a particular location, right? And it also assigns probability. Basically says, well, with probability 0.7, I should place this ad at this location. And then you look at the return. And the return might be $5. Now, if your policy mu puts higher probability on that particular action, right? Maybe it's a better policy, right? On the other hand, if it puts less probability onto actions that give you more negative return compared to the existing policy, then it would be better policy as well, right? So you're basically kind of saying, well, if I look at the ratio of these two policies, is my new policy assigning to actions that give higher returns higher probability, and assigning actions to, you know, the actions that give me less probability to the actions that give you less return or negative return, right? So that's kind of the idea behind importance sampling. Let me show you just quickly how importance sampling operates. How many of you have seen importance sampling? A few. How many of you have seen sequential importance sampling? Okay, less. So importance sampling is an extremely simple method, but there are extensions of these methods, something called sequential importance sampling, which allows you to even build better sampling, these importance sampling algorithms. But the idea is the following, just so that you have an understanding of what it does. You draw independent samples, Z1 up to Zn, from distribution to approximate this expectation. Okay? So sampling, importance sampling is all about approximating expectations, high-dimensional expectations, right? And the way you do it is you're basically saying, I can approximate this expectation by taking the average, all right, of the value. So if I sample according to distribution P sub z, and I just look at the average of the function at those points, then I get some estimated f bar. And I can prove that the expected value of f equals the expected value of f bar, or f hat here, my estimator. So I have an unbiased estimator here. Okay? So the estimator has the correct mean. It's a heavily used method anytime you have, you know, some high dimensional integrals that you need to estimate. You can construct an importance sampling algorithm from it. Now the variance, if you look at the variance of the estimator, it has this property. So the variance decreases as 1 over n. Okay? And the accuracy of this estimator doesn't depend on the dimensionality of the space. So the space itself could be very, very high dimensional. If you look at this, it looks a little bit magical, right? You have this huge dimensional space, and somehow your variance is actually shrinking as 1 over n, which is pretty significant. Like in many cases, if you have like 100 samples, you can have a very accurate estimator. Even though this integral could be, you know, 1,000 dimensional or 10,000 dimensional integral. Now there are some caveats. Problem one, we may not be able to draw independent samples. Okay? So if you can't draw independent samples from P of Z here, then it becomes a problem. In many practical cases that we're going to look at later in the class, you can draw exact samples. In our case, we're going to see that we can for the policies because we're working with something simplistic, but in many cases you can't. So then you have to resort to something that's called Markov chain Monte Carlo methods, right? And now it requires many, many samples to actually estimate these expectations. Problem two, if f, your function that you're trying to estimate, is large in regions where P of Z is small, and the other way around, then the expectations may be dominated by regions of small probability, right? So for example, you know, here, the probability under your P is small, but the value of the function is high. So once in a while, when you get a sample from here, right, you have a very high value of f. And that will throw you away. Basically, the variance is going to be increasing, right? Does that make sense? Now, the idea to the importance sampling, let's say we have an easy-to-sample proposal distribution Q. So here we have to be able to draw samples from P of Z. And in many cases, as we'll see, we can't really do that. So let's say we have an easy-to-sample proposal distribution Q such that these assumptions hold. And if you think back, you can now start connecting when we have two policies. One policy could be Q, the other policy could be P, right? So we're trying to evaluate one policy with respect to another one. So let's say we have an easy-to-sample proposal distribution Q, and P could be some hard distribution that we can't really sample from. Then I can do the following. I can divide and multiply by Q of Z, right? So I can do this operation. And then I can convert this estimator into this problem. And this is known as a simple importance sampling estimator. Because you're drawing samples from Q, think of it as an easy-to-sample from distribution, or a policy that you can sample from. And now you're looking at the ratio of P over Q and the value of the function at that particular point. In terms of expectations, we're okay, right? So the quantities P over Q are known as importance weights, right? It's measuring how much P is relative to Q. If Q has smaller probability than P, then the weight will be higher. If Q has larger probability than P, then the weight's going to be lower. Okay. So in this case, just to illustrate, this is an example of Q. Maybe it's a Gaussian. We can sample from the Gaussian. And you have some P, which is complicated distribution you can't sample from. But you can still evaluate expectations. So let's the proposal be of the form. Q is going to be Q tilde divided by Z. So Z here is going to be our normalizer. And Q tilde is going to be unnormalized probability. In many cases, for many distributions, you can actually compute unnormalized probability. But in many cases, it's very hard to estimate the so-called partition function or the normalizing constant. Right? Imagine this complicated distribution. It's easy to evaluate its unnormalized probability, but to be able to compute normalization constant so that the distribution sums to 1 or integrates to 1 is actually difficult. So if I look at the expectation of the F, I can write it down this way. I can multiply and divide by Q. And I can write it down as the ratio of partition functions and this quantity there. Okay? Right? Everybody sees that? So what do I do here? How do I compute these partition functions? So now I can say, well, this integral is going to be approximated by taking the ratio of unnormalized probabilities, or look at the importance weights, where samples are drawn from Q, but now I have this ratio of partition function that I can't evaluate. But it turns out you can use the same weights to approximate the ratio of partition functions. So you can say this ratio of partition functions can be written as such. I can rewrite it as the ratio of P tilde over Q times Q, and I can write it essentially as the sum, as the average of the weights. Right? So what it comes down to is it comes down to when I'm estimating my function f using importance sampling, I'm going to draw samples from my proposal distribution Q. I'm going to compute these importance weights, which the ratio of unnormalized probability, something that I can do, divided by normalized importance weights. So it's kind of making sure that all of these things are always going to be below 1 and they're going to sum up to 1. So this is sometimes it's called, it's the weighted average where these weights are normalized and you get the expectation of f. It's a very neat trick for basically saying anytime you try to estimate an expectation of some function f, and your expectation, you're trying to estimate expectation with respect to some probability distribution that you can't sample from. You can't evaluate. The only thing you can do is you can evaluate its unnormalized probability, which is in many cases you can do, right? And so now if I draw samples from my proposal distribution Q, I compute these importance weights, these ratio of unnormalized probability, which I can always do, take the weighted average, and then I get my estimator. Okay? And then there is a whole bunch of different algorithms that extend this method using annealing. If you've heard about annealed importance sampling, if you've heard about sequential Monte Carlo methods, there's a whole bunch of extensions of doing that, right? So I just wanted to give you a little bit of introduction into importance sampling just because we're going to be using it in a very, very basic form. Okay? So when we do importance sampling, it's hard to estimate how reliable the estimator is. And you will have high variance if the proposal distribution is small in a region where this quantity is large. Right? Because what happens is that you're going to be dividing large number by very small number. And if you divide large number by very small number, what do you get? You get a very large number. You get an even larger number, right? And when you're averaging things, imagine that you're averaging numbers and once in a while you have this huge big number that you're averaging over, right? And so now you can have a very unstable estimator. And here's an example of just one-dimensional Gaussian where you're using Gaussian distribution as a proposal distribution. And here you're trying to estimate your target distribution as a Cauchy distribution. A distribution has heavy tails. So even after 1 million samples, the estimator hasn't converged to the true value. Right? So here what you're seeing is that after 1,000, here you basically looks like you're converging and then it just jumps again. And it looks like you're converging again and just unstable. And in this case, after a million samples, you still haven't converged to the correct value. And this is one-dimensional example. Right? This happens if your proposal distribution doesn't have heavy tails, like a Gaussian. You basically have exponential probability of sampling in the tails. Cauchy distribution, which is what you're trying to estimate, which is your target distribution, has heavy tails. Right? So once in a while you have this big instability. And this is an example of using Cauchy distribution as a proposal, in which case after 500 samples you're basically converging. So the reason why I'm pointing this out is that when you're looking at offline policy evaluation that we'll see right now, you have to be very careful what distributions you're choosing and how you're actually handling it. Okay? Because these estimators can be very, very unreliable. So now, importance sampling ratio. So how do we compute the importance sampling ratio? So the probability of the rest of the trajectory S on the policy pi has this quantity, right? So we're computing the probability of taking action, getting the next state, taking next action, and so forth, right, on the policy pi. It's given by a bunch of these probabilities. The probability of taking the action, probability of going to the next state, taking action, and so forth, which I can summarize as the product, these quantities. Okay? Now, importance sampling, each return is weighted by the relative probability of the trajectory under the target and behavior policy, right? So this is your target policy, and this is your behavior policy. Think of it as a new policy that you're trying to evaluate. Right? Now notice what happens here. These quantities will be cancelled because you're working in the same environment. Both policies are working in the same environment. So that's kind of nice because there is no way for you to compute what these things are unless you know precisely what the model is, right? And what's the distribution of possible policies. So that's kind of nice. It's kind of equivalent to having partition functions being cancelled out when you use importance sampling, right? Essentially, that's exactly what's happening here. So now you're just looking at the ratio of the target policy versus the proposal policy, right? And you're looking at the ratio of the two. And as I mentioned before, what you want to do eventually, you want to say, well, does my policy assign higher probability, for example, for actions that lead to higher rewards? or does it assign low probability to actions that lead to low rewards, right? So that's how you're trying to do evaluation. And this is called importance sampling ratio. All importance sampling ratios have expected value of 1. So that should be trivial, because an expectation, if you take an expectation with respect to mu, things cancel out and you get 1. Okay? But the importance sampling can have high or even infinite variance. So you have to be careful how you apply it in practice. Right? So now, how do we use importance sampling? So we can use ordinary importance sampling. We can form the following estimate. Let's look at what this estimate is. So this is the value of the state. It's the weighted sum of your returns weighted by this importance sampling ratio divided by the total number of visited states. And I'll show you what I mean by T sub S. So T here, the capital T, is the first time of termination following time T. So you start at time T, you start at a particular state S, you go up to capital T when the episode ends. The return after T up to or through time T, right? This is kind of how much reward you're getting as you're executing that policy. And this is every time. This is a set of all time steps in which state S is visited. Okay? Let me give you an example. So imagine that, let me see, you start at state 4, you terminate, you start at time 4, you terminate at state S, you terminate at time step 9, right? So T sub 4 is 9. And then you start at state S again at time 20, and then you terminate at time 25. So think of it as follows. You're running the thing, you start at a particular state, you're executing your policy, you're terminating. You're running it, you're executing your policy, you're terminating. So you have these numbers, state S at time 4, you terminate, state S at time 20, you terminate, right? So now the set of start states is 4 and 20, right? Because those are the times that you've actually started at state S, particular state S. And so now you can evaluate what the value is here, right? Okay? Yeah, you basically have 2 samples here. And you just average over those 2 samples. You can basically say, I run this thing, I terminate. I randomly start at some other state, I run this thing, I terminate. But I happen to visit state S, so I'm starting from that state, I'm estimating, right? Because what you do in practice, you also look at this state. This might be state S prime, and you're looking at when it terminates. This might be state S double prime, you look when you terminate, right? And you're evaluating the value of every single state as you go along. And there is also weighted importance sampling, as we've seen. So there is a simple importance sampling, which just takes the average, a weighted importance sampling, which actually is computes the weights with respect to these importance weights, right? These rows, you can think of them as important weights, the ratio of the 2 policies. So in many cases, this estimate is actually a little bit better than the other one. So here's an example of infinite variance on the ordinary importance sampling. So this is a setting where, just to show you that when you're trying to do evaluation of the policies, offline policies, you can hit infinite variance. Let me just show you what this thing does. You have target policy, right? Your target policy is always go left. You start at state S, and your target policy is always go left. You don't go right. Right? Because if you go right, your reward is 0, and then you basically go to terminal state, so you don't get anything. So your policies always go left, and then with probability 0.1, you get +1, and you go to the terminal state, and with probability 0.9, you get nothing, and you go again to state S, right? And then you try again, and then you try again, up until you get the reward 1. The discounting factor is 0. Okay? Seems like this is a pretty good policy, right? You're basically trying to go left up until the point with some probability you get +1 and you go to the terminal state. Now imagine you have other policy, the soft policy, that basically says the probability of left is 1/2, the probability of right is 1/2. Okay? So now you want to estimate this quantity here. This quantity is going to be 0 because probability of right is 0. And this quantity is going to be 2 because probability of left relative to mu of probability of left is going to be 2. Right? So this is the ordinary importance sampling, which is to say, you're executing multiple trajectories. So you start at state S, and then you're executing left, you get 0, you get back to S, left, 0, and so forth, and up until you hit the terminal state. Same thing happens here. Up until you hit +1, you get the terminal state. Okay? So you can just look at this little dynamics. But what I want to point out here is that in this case, in many cases, you can see that you have this bizarre behavior. So it's very hard to do proper evaluation of the policy, right? Because once in a while you hit these high numbers and it's very unstable, even after 100,000 iterations. Or if it's even on the log scale, so it basically doesn't converge. Okay? This is also an example of policy estimate of the value of a single blackjack state. This is what happens to the ordinary importance sampling as the number of episodes scales, and this is what happens to the weighted importance sampling, right? So you can see it's much more stable. In many cases, it can be much more stable. Okay? This is just, I'm running a little bit short on time, but this is something that you can look at yourself. This is just a very simple way of actually doing incremental of policy every single Monte Carlo evaluation. And again, this has to do with the fact that you're computing these importance weights, right? So you're computing importance weights with respect to pi policy, which is some arbitrary target policy versus mu policy, right? So you can get better estimates of the Q, right? So this is just another example where the target policy is greedy and deterministic, and behavior policy is soft and epsilon greedy. So you can do policy evaluation that way. Okay? This is pretty straightforward. It just gives you a way of computing these weights. You're maintaining these weights, and then you're doing update of your Q function, incremental updates of your Q function, right? As we've seen, kind of taking the average. So if you just wanted to do it 1/k, you could do that. But here you're using importance weights, right? So let's look at a little bit of a summary. So Monte Carlo, and again, we'll come back to Monte Carlo again in this course. This is a very basic introduction to MC methods. You have several advantages. You can learn directly from interaction with the environment. You can simulate from the environment. You don't require having a full model, unlike in dynamic programming setting. If your environment violates the Markovian assumption, typically Monte Carlo methods are pretty robust to that, right? Because you're simulating your world and you're trying to estimate the best that you can. One issue, you're basically maintaining sufficient exploration, and you can learn directly from interacting with the environment. And we also looked at the distinction between on-policy and off-policy methods, right? Remember, on-policy methods is you're trying to learn something about the policy that you're just executing, sort of continuous policy. Off-policy methods is you have a policy that sits in your production, and you have a different policy that you're trying to evaluate against target policy. And we also looked at the importance sampling for off-policy learning, right? Paths to policy. So this is kind of like a mental picture for you to keep in mind. And you should also look at Sutton and Barter's book, because they go into this in details. Paths to the policy. So there is a simulation-based RL. Think of simulation-based RL as that you have some model, right? And then you get experience from that model. So you get samples from the model. And then you're using direct reinforcement learning methods to estimate the value function, and you get the policy. Okay? You also have model-based RL. which takes a different path. You have some experience from the environment, and then you're actually building the model of the world, right? Once you have the model, then you can basically go directly to evaluate the value function. Because if I know everything about the world, I can compute expectations and everything, right? I can compute transition probabilities, what the next state, given my current state in the action, I can take an expectation with respect to that, and I can just go directly and evaluate my value function and then get me the optimal policy. Oh, sorry. One last thing before we quit, I just wanted to point out that, as I mentioned before, there are a number of people advocating this approach. Think of it as a model-based reinforcement learning. You want to build a model of the environment. This is more of a model-free approach, right? You have some model, you don't really estimate it, but you get experience from it, right? You get samples from it. Once you get samples from it, I can try to directly go and estimate what the value function is, right? So depending on which problem you're working with, it still is a debate, because you have people who basically say it's kind of silly to do this, right? Model-free reinforcement learning, sometimes it works, but you have no idea why it works, especially once we start plugging deep learning into it, because then we're gonna stick deep learning methods in here, and they work remarkably well. Model-based approaches are you actually trying to build the model of the environment, and then based on that, figure out. And it has advantages and disadvantages, because in many cases, building the model of the world is super hard. And you basically can't really, put all the regularities of the world. So, okay, so next class we're going to look at temporal difference learning and sort of contrast dynamic programming, Monte Carlo, and TD learning.